Hello, we are Maddie, Abby, Will, and Bruno, and we'll be sharing with you a generalized model for classifying emotions via EEG based topographic brain mapping. Mental health has become one of the most prominent areas of public health in recent years. As a result, mental health counseling services have become more popular than ever before. However, according to a study conducted in 2015, up to 93% of patients lie at least once per therapy session, primarily about questions and topics they find uncomfortable. These patients don't intentionally mislead their therapist, but rather choose to suppress thoughts of fear, sadness, embarrassment, and other such feelings. By not conveying their true emotions, they stunt their own growth and limit the efficacy of counseling, which results in the therapist not knowing how best to work with the patient. Therefore, a non invasive metric for gauging a patient's true emotions would improve the quality of the patient's sessions and, by extension, their mental health. The model we are discussing today is entirely novel, both in its method of categorizing emotions from brain maps and in its implementation as a real time tool during therapy sessions. Additionally, our novel method may allow for successful intersubject modeling of a generalized emotion classification framework, something that is currently a significant barrier even in the most state of the art applications of EEG based emotion classification. To understand the significance of this model, we'll first discuss the technology driving the data. EEG, or electroencephalogram, is a non invasive technique for quantifying surface level brain activity. The electrical activity in the brain has a wide frequency range, but the beta wave range of 12 to 30 Hz is of interest for this application, as there are known variances here in brain activity that are associated with different types of emotions. Various methods of visualizing EEG data have been pursued, but one largely unresearched area is using the EEG electrodes placed around the scalp to create a topographic map of brain activity, bringing to life the vast network of activity across all parts of the brain. This is our novel approach. By developing these topographic maps for various positive and negative emotions, then classifying them using our algorithm, we are able to identify patterns of brain activity associated with specific emotions. Our objectives are as follows. First, to identify patterns in topographic organizations for each emotion. Second, to classify emotions based on the brain topographic maps that we create. Third, to obtain our desired accuracy threshold value for an individual subject. And last, to train and test the model on additional subjects. We hypothesize that accurate classification of emotion will be possible for an individual subject with an accuracy greater than or equal to 85%.
For our project, we utilized Imagined Emotion EEG data from a study conducted by Julie Anton back in January of 2021. The study included 34 subjects who were taken through voice recordings of 15 different emotion narratives, each containing a positive or negative valence. You can see which emotions were classified as either positive or negative valence in the top right table. As they listened to the various recordings, the subjects were asked to push a button when they started to feel the emotion described. These emotion recordings lasted up to 3 to 5 minutes. Ideally, the subjects felt the desired emotion throughout the whole duration of these recordings. All the subjects in this study are classified as healthy and normal adults. The data was recorded using 256 EEG electrodes at a sampling rate of 256 Hz.
In order to create topo maps and classify the emotions, we first load the EEG data into Python, then we divide the samples into 1-second windows. We chose a window size of 1 second because we want a fast response time when applying this model into therapy. Then we calculate the band power for the frequency range of beta waves for each channel. Finally, we load the electrode locations and map them to a 24 by 24 image in which the pixel values are the calculated band power for each channel. Then we complete the missing values with cubic interpolation, split the dataset into train and test, train a CNN model with the trained datasets, and evaluate the model with the test dataset. In this project, we chose CNN model topology because we wanted to use fewer parameters than if we use DNN to classify the image. So we input the 24 by 24 topo map into a convolution layer using A filters and a 3x3 kernel. Then we perform max pooling to reduce the number of parameters. And then it goes through another convolution layer, but it's time with only 5 filters. Then we flatten the output of that layer so it can go through a dense layer with 16 neurons. Finally, we have an output layer that uses a sigmoid function to give a score between 0 and 1. A score lower than 0.5 is classified as a negative emotion, and a score higher than 0.5 is classified as a positive emotion.
When training our model on the individual imagined emotion EEG data, we utilized 60% of the dataset for training and 40% of the dataset for testing. The figure on the left represents the training accuracy of our model for each epoch. There was a hyperbolic curve for training accuracy versus the number of epochs. Our training accuracy peaked at around 97.3%. There were minimal improvements in training accuracy after the 600th epoch. Since we were able to obtain the true emotional states for our subject from the imagined emotion dataset provided, we created a confusion matrix on the test dataset. The confusion matrix, presented on the right side, gives insight into the performance of our emotion classification model. The two squares on the left side equate to the number of times our model predicted a negative valence emotional state, whereas the two squares on the right side equate to the number of times our model predicted a positive valence emotional state. The upper left square represents the number of times our model correctly predicted a negative emotional state, and the bottom right square represents the number of times our model correctly predicted a positive emotional state. The bottom left square represents the number of false negatives, and the upper right square represents the number of false positives. In effect, using the confusion matrix, we calculated the sensitivity, specificity, and accuracy values of our emotion classification model. Our subject-specific model achieved a sensitivity of 0.9, the true positive rate, a specificity of 0.88, the true negative rate, and an overall accuracy of 0.892.
After creating a high accuracy individualized model, we then moved on to seeing if we could classify emotions with other patients and create a more generalized model. We had 7 subjects and used 5 of them for training and an additional 2 subjects for testing. After 35 epochs, our model reached a train accuracy of 79.67%, so then we went on to testing. When testing the generalized model, we were also able to obtain an accuracy of 77.39%. We are very happy with these accuracies for the generalized model. Since the model was distinguishing between positive and negative valence only, we wanted to target for high accuracy value of 0.85. Additionally, other studies conducted show that most groups had accuracy values around 0.8. By increasing the standard of accuracy for our model, we aim to present a new and improved model for emotion classification. We concluded that our hypothesis is supported and that an accuracy of 89.16% was achieved when classifying emotions for a singular subject. When using topo maps to classify emotions with other subjects in a more generalized model, we achieved an accuracy of 77.39%. While the accuracy when testing our algorithm on a single subject is very high, the accuracy of the more general model has decreased a little bit. This aligns with current knowledge of the limitations in the field. This algorithm needs to be manipulated further in order to prove accuracy and become a realistic tool for clients. Despite the success of this model, there's still a lot of improvements to be made. Additionally, we would like to use the model to create 3D brain maps to help improve the accuracy. Other than that, we also would like to target using our algorithm to be applied to patients in non-neurotypical demographics, such as individuals with autism spectrum disorder. Since people on the autism spectrum have trouble accurately identifying emotions in themselves and others and expressing how they feel, our method and application could be extremely useful for them, their caregivers, and their doctors. To achieve the desired accuracy for this additional implementation, more EEG data needs to be taken and run through the algorithm. Currently, there are no available EEG data sets for patients with autism spectrum disorder. After obtaining these new data sets, we'd be able to see how accurate our project is for subjects outside the set of healthy adults. Another significant long-term priority is implementing this project in a real-world application. A simplification of our results to create a clear protocol for therapists to apply in their practice would make it necessary for a fully successful application. One direction this could take is more corporate, but many low-cost consumer-directed EEG headsets currently exist on the market, and developing a partnership with these companies could increase the accessibility and affordability of this implementation. Thank you.